Lesson 2.3 is about acceleration. Please pause the videos and look through the 3 objectives that we're going to be going through. Acceleration is defined as whenever a particle's velocity changes. So anytime you go faster in a car, you accelerate in the positive direction. Anytime you put the brakes on in a car, you decelerate in a negative direction. Just so you know, sometimes this is hard for people to wrap their head around. You can be negatively accelerating, like slowing down, but still have a positive velocity. It's just that your velocity is getting slower, therefore your acceleration is negative. It doesn't mean your velocity is negative, just that you're slowing down. Like velocity, acceleration can come in 2 forms. So average acceleration, just like we used to have average velocity, and instantaneous acceleration, just like we would have instantaneous or instant velocity. Okay? For motion along an x-axis, the average acceleration over a time interval is defined as delta v over delta t. So yesterday, we had that v equaled delta x over delta t. Today, we're going to take that one step further, and average velocity is delta v over delta t. So if we had the final velocity minus the initial velocity, and the final time minus the first time, that would work out. That's exactly how that works. Again, so we can kind of conclude here, if you guys can wrap your head around your Algebra 1 skills, acceleration is the slope of a velocity time graph. Using dimensional analysis, we can determine the units on acceleration. So I'm going to teach you how your units work out. Well, we know that acceleration is a velocity over a time. We also have learned that velocity is a meter over a second and a time is a second. This is units now, okay? So in our Algebra 1 skills, we'd throw that S on the bottom, so our units are a meter per second squared. That's acceleration. And we can conclude our units are meters per second squared. All right? Knowing our units is very important as we approach everything we do in physics, okay? Example 1. Saab, is that how you say that? Is that how you say that car? Is it S-A-A-B? Is it Saab? Saab.
You're like sobbing.
Okay, I'm way too poor to own one of these. Okay, so Saab advertised, that's I'm not deleting that. Advertises a car that goes from 0 to 60 in 6.2 seconds. What is the average acceleration of this car? I apologize. This should not. Let's not do miles per hour there. Can we please change that to meters per second? My bad. I'll fix that for next year's kids. Sorry. Average acceleration. So we're going to do acceleration average, just like that. Would you mind going to the bathroom and getting a paper towel?
Oh, yeah.
I'm sorry, sweetie. You guys are probably having a hoot at home listening to this. All right, so we have delta V over delta T. Working it out, we have V2 minus V1 over T2 minus T1. So V2 is the final velocity, 60, minus V1, original velocity, and time 2 is 6.2, and the beginning of the problem was 0. So we end up with 60 over 6.2, which is 9.68 meters per second squared. Okay? I know I'm not following the 4 significant thing right now just because I've already done the notes and we can work on that a little more in class. This is just what my answer key has over here, so we're just going to go with it. Example 2. An airplane has an average acceleration of 5.6 meters per second during takeoff. How long does it take the plane to reach 150? Now what I am going to do up here is, if we know this is a major formula, then I guess we better be able to say 2 other things. We should be able to say that the change in velocity equals the average acceleration times delta t, their change in time. And I guess if you really wanted to, you could just probably write AT and know what that means. And vice versa, if we solve this equation for t, we should say the time is the change in velocity divided by the acceleration. So here we do have 3 overarching. This will go on your sheet of paper for you to reference when you work on your homework. So we want to know how long. So that means we're going to use our t equals equation, and that would be t equals delta v over acceleration. So let's take a look. time equals, well, we knew that it was started at 0 because the takeoff, I mean, an airplane sitting still, and then it reaches 150. So it would end up being 150 minus 0. So it's 150. We have the acceleration given to us as 5.6. When we divide that out, we get 26.8 seconds for our time. All right, first page is done. The next problem is going to be a little bit of a doozy, but that means it's going to be exciting. A train moving in a straight line with an initial velocity of 0.5 meters per second accelerates, so it's going to go faster, 2 meters per second squared for 2 seconds. It then coasts with 0 acceleration for 3 seconds, and then it accelerates at negative 1.5 seconds squared, so it's going to go slower for 1 second. What is the final velocity of the train? What is the average acceleration of the train? So we have 2 questions, but before we do that, I'm going to do like my little free body diagram up here to help me make sense of the whole thing. So here's the trip of the train, and let's see, it says it's moving in a straight line, an initial velocity, so at this dot, it has a velocity of 0.5 meters a second. And it's also at this dot, it's accelerating for, so I can write, it's accelerating at 2 meters per second squared, and that happens for 2 seconds. So oddly enough, this dot happens at t equals 0, and then this acceleration happens up until t equals 2. So at t equals 2, something new is going to happen. It's going to have 0 acceleration. So I'm going to write acceleration equals 0 meters per second, so it's coasting. And that's going to go for 3 seconds. So that's going to take us to t equals 5 seconds, because you add 3. And then it's going to accelerate. Now our acceleration is going to change to negative 1.5 meters per second squared. That's going to happen for 1 more second. So that's going to take us to t equals 6 seconds. So I just kind of made this a little bit too long here. And that happens for 1 more second. What is the final velocity of the train? So I'm looking for velocity here. Okay, what is the average acceleration of the train? So let's take a look at a couple of things. Let me kind of wrap my head around some stuff before we move on. So when I was kind of sitting here thinking about it, I would really like to know what the velocity is here, and I would really like to know what the velocity is right here. So let's go ahead and try to figure that out, okay? So let's call this, we'll call this one velocity 1. I'm going to try to find velocity 2. Okay, so this is like for the first part of the trip. So I'm going to label this as the first part of the trip, the second part of the trip, and the third part of the trip, okay? So looking at the first part of the trip, I want to figure out what the final velocity is, okay? So I know that one of the equations we talked about today was that the change in velocity, if I flipped back over, the change in velocity is the acceleration times the time, okay? So if I do acceleration times time, change in velocity equals the acceleration during part 1 is 2, and the time that elapses is 2. So my change in velocity is a total change of 4, okay? So if my velocity 1 was 0.5, I know the change in velocity is velocity 2 minus velocity 1. So that would be the change of velocity being 4. Velocity 2 is what I'm trying to solve for, minus my original velocity is 0.5. When I add that to the other side, I have velocity 2 should equal 4.5. So it's pretty important to get that velocity right there. 4.5 meters a second. Okay, now let's try to figure out what the velocity here is. So let's call this one velocity 3, okay? So I'm just going to look at the second part of the problem. I want to see that as an isolated event, okay? So number 2, I know change in velocity equals the acceleration during time. So the change in velocity is going to equal my acceleration of 0 times my time of 3 seconds. So my change in velocity is going to equal 0. So if that just means that there's 0 change, which means if I call that my velocity 3, velocity 3 isn't going to be any different than velocity 2 because it's not changing. So velocity 3 is also going to equal 4.5 meters a second. So let's go ahead and label that up there. And that makes sense if you're not accelerating, that your velocity stays constant. I would also like to figure out what my velocity is back here. Okay, so step 3, or excuse me, part 3, I know that my change in velocity is my acceleration during that time times my time. So my change in velocity is, and the acceleration here is negative 1.5, and the time that elapses is just 1 second. So my change in velocity is negative 1.5. Now, this time, this is going to be my velocity number 4. So I'm going to write that velocity 4, or maybe I should write change in velocity equals velocity 4 minus velocity 3. And my change of velocity is negative 1.5 for my equation above, of velocity 4 minus 4.5. If I add 4.5 to both sides, I get 3 for velocity number 4. So that's 3 meters per second for my ending velocity. Okay? So let's take a look at our questions now that we figured out kind of the bits and pieces there. It says, what is the final velocity of the train? Well, I'm pretty sure we answered that pretty good. 3 meters per second is the final velocity of the train. That's part A. That's like, where does the train end at? It ends at 3 meters per second. So that's part A. Part B says, what's the average acceleration? So this is for B. They want us to find the average, A for acceleration and AVG for average. So average acceleration is the change in velocity over the change in time. Now, the hard part about this problem is that we kind of have to talk about the change in velocity because the velocity changes so many times. So the total change in velocity is the first change in velocity that we encounter. And then the second change of velocity, we have to add that on that we encounter. Now, I'm not just adding the velocities, I'm adding the changes in the velocities plus the third change in velocity. So the total change in velocity are the individual changes added up. So we have change in velocity equal, let's go to part 1. Part 1, the change in velocity was a 4. So the first part had a change of velocity of 4. The second part had a change of velocity of 0. The third part had a change of velocity of negative 1.5. When you add those together, you end up getting a total change of velocity of 2.5 meters per second. That's a tricky concept. So now, let's see, the final question says, what is the average acceleration? We're getting really close. So we have acceleration average equals my total change in velocity, all the different changes added up, divided by the entire time. So it took 6 seconds. If you look at the picture from 0 to 6, I had a 6-second change. When you divide that out, 2.5 divided by 6 on my paper, I have 0.42 meters per second squared. So overall, my acceleration averaged to be a positive acceleration when considering the chunks of time it took each time. All right, let's take a look at example 4. A ferry makes a short run between 2 docks, one to that place and the other one to that place. The ferry approaches the island traveling in the positive x direction. Its speed is 7.4 meters per second. If the ferry slows to a stop in 12.3 seconds, what's its average acceleration? As the ferry returns to the dock, that should say as the speed is 7.3. If it comes to rest in 13.1 seconds, what is the average acceleration? All right, give me 1 second to try to find my notes on this one. I didn't need to look at my notes. We know this. Silly me. Okay, part A. Ready? So they want the average acceleration for the thing that's happening, okay? So it's going to slow to a stop in 12.3 seconds. Well, that's our time. So we can put that on the bottom. Now, if it's going to slow to a stop is 0. So we can do 0 minus, where did it start at? Oh, well, here it started at 7.4. So we have negative 7.4 over 12.3. So the average acceleration is negative 0.6 meters per second squared. Part B. They want the average acceleration again. So let's see what it says. As the ferry returns, its speed is 7.3. If it comes, okay, now we have to be careful because it's going to be returning, right? This way we define as being positive. Oh, wait. Give me a sec. Where is it going to? If the ferry slows, if the ferry approaches the island. Okay, we're actually going to make this way be positive, and we're going to make this way be negative, okay? Which is opposite of how our mind usually works, but we're going to start at the beginning of the problem. So the beginning of the problem, it's going this way, so we're going to make that our positive way, okay? So oddly enough, this negative actually means that this one's accelerating to the right. Okay. As the ferry returns to the dock, its speed is 7.3. So because it's going to the right, we may as well go ahead and indicate that that's a negative 7.3. It comes to rest in 13.1 seconds. So that's our time. What is the acceleration? So it's going to come to a rest. So we do 0 minus negative 7.3. So we get positive 7.3 over 13.1. Divided out, we get a positive 0.56 meters per second squared. Now the reason it's positive is because it's traveling, like the average acceleration ends up pulling it backwards, okay? So it's backwards to the left in our case because it's pulling it, like as it's slowing down, it's pulling it left. As we let the time interval become increasingly, we're going to move on now, okay? That's like a different little concept here. We're going to talk about instantaneous again, just like we did with velocity yesterday. So just like we let the time interval become increasingly small yesterday, we can also do that today to define instantaneous acceleration. Mathematically, we represent this as such. We write that limit as the change of t gets infinitely close to so you really look at a certain time frame. That's going to end up equaling delta v over delta t, which, if that's slope, that means it's derivative. So you take the derivative of the velocity with respect to time. And we did this yesterday. Please remember that the derivative of a position equation is velocity. Now add to your memory bank that the derivative of a velocity equation is an acceleration equation. So an interesting result can be seen because we can relate that yesterday we did the derivative of a position graph. So maybe we should write this down. Velocity, you'll need this for your homework, is the derivative of a position equation. And up here, right, acceleration is the derivative of velocity equation. So write these things on that sheet that you have, kind of your cheat sheet for your homework. All right, let's take a look and play this out. Okay, I'm going to talk in calculus language here if it's too much for you to handle. As long as you kind of understood the last two things we said, you're good to go. But if I tell you that, and I have, acceleration is the derivative of a velocity in respect for time, if I said, hey, why don't you just go ahead and like move that velocity to the side here, we still have the same equation, don't we? And yesterday we learned that velocity is the derivative of x in respect to time. So if we work this out, we end up getting d squared x over dt squared. Now, maybe that doesn't ring like a huge bell to you guys or anything, but here's what this means in words. The acceleration of any particle, of a particle, at any time, let's write at any instant time, at any instant is good enough, is the second derivative of the position equation in respect to time. And you can kind of see that playing out because here's our second derivative of our position equation in respect to time. All right, let's go ahead and now take a look at some of these graphs. Can you see how this first graph is a velocity time graph? So if you were traveling on this line, the slope of this top line is 0.25. So anywhere on this line, the acceleration is going to be 0.25 because it's simply the slope of that line. And that's what a derivative is. It's the slope of a line. And then if you look at this one, the slope of this is a straight line. So whatever this slope is, which is negative 0.5, that's going to be your acceleration. Now let's say you kind of have like a topsy-turvy graph here, okay? This graph is not just like simple, basic, easy to read. This particle is traveling on this really weird curved path. It looks like the velocity is going up really fast, and now the velocity is slowing down. Now the velocity is 0, and now the velocity is negative, and then it looks like it's going to be 0 again. If you wanted to find the average acceleration between 2 points, you would find 2 points like this, and you would do the old school slope formula. And that would find you the average acceleration, okay? So for average acceleration, let's go ahead and write average acceleration, use 2 points. Okay, but for this instantaneous acceleration, you're going to need to use that tangent line thing we talked about. And the tangent line is where you have to find the derivative. So if you want an instantaneous acceleration, that's when you need to use your derivative. Example 5. Suppose the x velocity, Vx, of a certain car at any time t is given by this equation, 60 plus 0.5 t squared. So if we eliminate the units, we end up with the velocity based on x is 60 plus 0.5 t squared. Okay? So I already have a red flag that my velocity is an equation. If I take the derivative of this equation, I will have my acceleration equation. You might want to restate that sentence. We're going to do that in part D, by the way. Part A. Find the change in x velocity of the car at time interval 1 equals 1 and time 2 equals 3. So part A will not be crazy hard. We're just going to plug in, they want us to find the x velocity in 1 second. So we're just going to plug 1 in for our t because t is 1 second. When we solve that out, this velocity equals 60.5. So that wasn't terrible. This is meters a second. Let's find velocity and I'm going to call that velocity 1 because it was in 1 second. Now let's do velocity 2. The second velocity is going to be 60 plus, they want us to plug in 3 seconds. So 0.5 times 3 squared, we end up getting 64.5. And you should double check the math if you're watching this video to make sure you know how to get that. So part A says, hey, what's the change in velocity between those 2 seconds? So the change in velocity is the second velocity of 64.5 minus the first velocity of 60.5. Change of velocity is 4 meters per second. So that wasn't too terribly difficult. Let's take a look at part B. Part B says find the average x acceleration in this time interval. Okay, so that is average acceleration. That's really important that you hear that it's average because that means they want you to find delta v, which we just did, over delta t. So our delta v we already found is 4 meters per second, and the time change was 3 minus 1, because it was 3 seconds and 1 second. So that's 4 over 2, so it's just 2 meters per second squared. Remember, this was average acceleration, not instantaneous acceleration. All right, now Patsy is going to go ahead and really hone in on your algebra skills here. It says find the instantaneous x acceleration. So we have this word instantaneous. When you see this in your homework, just automatically find the derivative. It makes it a lot easier. Find the instantaneous x acceleration at t equals 1 by taking delta t to be 0.1, 0.01, and 0.001. So we're going to, so here's 1 second. Like 1 second happens here at my hand, right? So 0.1 seconds is like this much, and then they're going to say, okay, get smaller and smaller and smaller and smaller, and see what's happening to the acceleration and what numerical value is the acceleration coming to. So let's start by making delta t 0.1. So we're going to look at the difference between t equaling 1 and t equaling 1.1, okay? Because they want delta t to be a difference of 1, and they're asking us about 1 second up here. So in order to do that, we need to find our acceleration. Remember, and this we're unfortunately going to have to do average acceleration. So to do that, we need to find, I'm wrapping my head around it, give me a second. Okay. At t equals 1, we already know that the velocity is 60.5. So kind of put that in your memory bank, okay? Now, to find our acceleration, we have to go ahead and do at t equals 1.1, what's my velocity, okay? 1.1, my velocity is 60 plus 0.5 times 1.1 squared, which ends up being, I don't have a calculator. Here, I found one. Okay, so 60 plus 0.5 times 1.1 squared. Okay, so it's 60.605 meters per second. I'm doing this without my answer key. Are you proud of me? So the acceleration at this, with a difference of 0.1, the acceleration is going to be the change in my velocities. So the change in these two velocities that I'm pointing at. So I'm going to grab my calculator. I'm just going to do that on my calculator. So I'm going to subtract 60.5. So the change in my velocities is 0.105 over the change in my time. So these two times here, the change is 0.1. So right there, my tiny average acceleration for that small window of time is 1.05 meters per second squared. Now what they want us to do is they want us to do that exact same thing again. I might need to write a little smaller, but now they want us to do a delta t of 0.01. So if we need, that means we need t to be 1 because they're asking about 1 second. And we need the next t to be 1.01. So I know my velocity here. I already know my velocity at t equals 1 is 60.5. But to find my velocity here, I'm going to have to use my equation. And I'm going to have to do 60 plus 0.5 times 1.01 squared. And, oh geez, that's a really, okay, so I'm going to write 60. I'll move it here. That looks like a great spot for it. 60.51005 meters per second. So what we're doing is we're taking the time frame, we're getting closer and closer and closer and closer and closer and closer until it's instantaneous. We're going to see what it's yielding to. So the acceleration in this particular tiny time interval is the difference between these two. So that difference, if you want to see it worked out, you're just going to subtract 60.5. So 0.01005 over 0.01 is 1.005 meters per second squared. So we're honing it in, and guys, look how it's just, I mean, it's getting really close to a value of 1 at 1 second. But let's just double check that one more time with this next tiny time interval. They want delta t to be 0.001. So if that's the case, we know t equals 1. We know the velocity here is 60.5. So now we're going to do t equals 1.001. So the velocity is, let's plug that in. I'm plugging into this equation right here, just like I did in the last one. Plus 0.5 times 1.001 squared. Well, I hope I squared it last time. Oh, dear heavens, I feel like I didn't square it last time. I did. Phew. Okay, 60.5010005. So my acceleration in this time frame is going to be the difference of those. So 0.001000. How many zeros are there? 1, 2, 3, 5. Over 0.001. So I'm getting a tiny average acceleration, and you can see this number is just getting smaller and smaller and smaller, and that 5 is just moving further and further in the back. And I hope we can conclude that if we continue doing this, maybe for like 0.00000001, that's just going to keep tailing off, and we're going to approach 1 as an acceleration at this time. Now, part D. Everything we did in part C is literally useless because part D we can do super fast. We know velocity is 60 plus 0.5 t. Okay? So we should be able to say that the derivative of velocity is acceleration. So the 60, just like see ya, right? The 60 goes away. There was a 1 with this t. So what happens is this 1 comes down and it multiplies by oh wait, this was t squared. Okay, let's try that again. This 2 comes down and it multiplies with that 0.5. And the t, the exponent, goes down by 1. So my average my instantaneous, maybe I should write that, instantaneous acceleration is 1 t to the first power. So if they wanted me to find, let's take a look at part D. It says derive an expression, done, for the instantaneous acceleration as a function of time, done. Then find the acceleration, instant acceleration at 1 second and 3 seconds. I just have to plug that in. So for 1 second, I plug in 1 and I get 1, which, if you guys look how long it took us to get 1 down here. Look how much faster that was. So I'll write 1 second. I'll draw an arrow. Now for 3 seconds, watch how we don't have to, we could do 3 and 3.1, 3 and 3.01, 3 and 3.001, and do this whole thing again. Or we can just plug it in for that t, and at 3 seconds, it's 3 meters per second squared. Oop, put my squared on that one. All right, so what I really need you to gather from this example is that if you can take the derivative of a velocity equation, you will therefore have the acceleration equation. And then you don't have to bother with all this interval stuff unless it asks you to. I think we're almost done. The last part is this thing called G units. Have you ever seen like, oh, it has this many G's? Well, when we went to Disney this summer, and there was like 2 mission space. I don't know if you know that or not. There's a mission space orange and there's a mission space green, and like one has a bigger G force than the other, and like it depends if you get sick or not, which ride you want to go on. So I looked it up in the space. I wrote it down on my notes here. At Disney, the orange has 2.5 Gs versus the green. I don't think the green has anywhere near that. So it's like, what do people mean when they say the G force? So let me go ahead and tell you what it means. It is for very large accelerations. For very large accelerations. Okay. And it's pretty easy. 1 G force equals 9.8 meters per second squared, which, by the way, is the pull of gravity. So you always just kind of divide by 9.8, and that's your g-force, okay? So if you have a roller coaster that's going around a loop and it has this type of acceleration, express this in terms of g's, you would just take 28.2, you would divide it by 9.8, and you end up with 2.878 g's. And that's how many, that would be what they call the g-force on that particular ride. Okay, I promise we're almost done. This is the last page. Since acceleration is a vector quantity, the signs have a super significant meaning. Here is the incorrect language, okay? So when people say this, they're wrong. They say positive acceleration means the object's speed is increasing, and negative means it's decreasing. And negative means the speed is decreasing. It sounds good, but it is wrong. The correct scientific language is the sign of acceleration simply indicates its direction. The sign of acceleration only indicates the direction of the acceleration. Okay, if V and A have the same sign, the speed is increasing. If V and A have opposite signs, then the speed is decreasing. Please notice the use of the word speed instead of velocity. Okay? I'm not using the word velocity, I'm using the word speed. Mr. McBurney has some graphs and stuff that I think we're going to need to talk about, and I think those are just going to have to be talked about in person if you can remind me. Whew, we did it.